believe you're muted.
I can briefly introduce Oscar.
That'd be great.
So Oscar is a senior researcher at British National Lab. In the past, he's worked with NVIDIA and has worked a lot with sort of compilers and SmartNICs. And his research interests are programming languages, runtimes, and some of the topics that we'll talk about today, things like OpenSHMEM. And
wonderful.
Oscar
Thank you for that.
He can provide a better intro when he gets to his section. But
very sorry about that, Oscar.
That's okay.
So together they are going to lead a tutorial on leveraging SmartNICs for HPC and data center applications. So go ahead and get started whenever you're ready. Thank you.
Okay, thank you, Amanda. And thank you everybody for joining. We appreciate you taking the time to join this tutorial. We will note this is a tutorial that we ran last year in 2023. Some things have changed and improved. We also ran a version at supercomputing, and then we will have kind of a slightly updated version at supercomputing 2024. So we'll talk about the agenda, but I do want to acknowledge that we have kind of a large number of people that helped out. Unfortunately, everybody wasn't able to be able to join today, but we have obviously Rich Graham from NVIDIA, Antonio Peña from BSC, and Richard Vuduc from Georgia Tech, who helped out and advised on some of the content for this tutorial. Okay, so the first thing I want to try to do, and we'll see if this works, is do just a brief audience survey. So let me see if I can share this here. So we have a Mentimeter. If you'd like to try that, I put it in the Slack. Let me see if I can put it in the Zoom here. Okay. Thumbs up, so at least one person is here. Okay. So this is just kind of a survey to sort of understand our audience a little bit better. We also have at the end kind of an option to leave general comments. I know Hotend, probably has a mechanism for doing that, but if you'd like to give us feedback, or if there's something that we talked about that you think we need to change or improve, this Mentimeter will be in the Slack and the Zoom, and you're welcome to keep adding to that. Okay, let's go. Yep. All right. Okay, have you used a SmartNIC before? So this is just kind of checking to see is anybody aware of what is a SmartNIC? Have you used them? They're relatively new, so we understand not everybody has. Okay, great. All right, and I don't know why this thing keeps grading stuff, but just ignore that. So here we have a couple of people that say yes. So kind of the majority are like, what is a SmartNIC? So don't worry, here it's fine if you're not correct. I don't know why Mentimeter switched to wanting to grade everybody. Excuse me. So this next question, have you thought about using a SmartNIC? If you don't know what it is, then maybe not. Hopefully by the end of this tutorial today, you will have some idea of whether it's a good fit for the application that you're looking at. Okay, so yes. So people are at least aware that it exists and are thinking about it. Okay. Do you have any use cases? So we'll talk about a lot of the use cases today, but for instance, are there any applications you're thinking about? Do you think about it in kind of a security service type mechanism? Are you looking to do high performance computing? This is sort of free response if you have any thoughts. AI networking. Okay, great. All right, I like this one. NVMe over Fabric. Okay, we actually won't talk about that much today. I think maybe the previous tutorial mentioned that a little bit. Let's go check that one out. But definitely, we're happy to talk to folks about that. All right. Understanding network traffic and communication bound HPC apps. All right. Oh, great. Okay. Then I think we have sort of a vote. Do you have any use cases that you're interested in? So I believe this one is kind of asking you to sort of rank some of the use cases that folks might have. HPC. Okay. All right. Okay, so I think HPC is maybe it's popular. Okay, and then finally, if you had to rank these things, so here are some of the things that we'll talk about some of these things that you can do with the DPU. Which one would you actually want to do? You know, would you want to do kind of telemetry, monitoring, compression, optimize communication, security, run, you know, containerized applications, security encryption? Okay, great. Compression. Okay. We'll talk a little bit about compression today. Obviously, we'll talk a lot about communication. We won't spend a whole lot of time talking about multi-tenant applications, but we can kind of direct you to some resources for that. Okay. And kind of how we thought that might turn out, but this is sort of interesting to see sort of feedback from everybody. Okay. This one is just kind of a baseline. This is kind of an advanced question. So are you familiar with UCX or UCC? We'll talk about this as one of the enabling technologies, especially for the NVIDIA Bluefields that we'll be talking about. Okay, and this will be for Jeff Watt, who, you know, this will help him adjust his level of complexity. Okay, so probably a mix of folks there as well. And realistically, you probably have used UCX or UCC. If you use MPI, you just may not know it because a lot of times it's sort of you know, below the application layer that you normally interface with. Okay, and finally, are you currently doing anything with SmartNICs? This sort of ties in with the first question, but you know, just interested in if folks have any feedback there. Okay, great. All right. Okay, so I love to see the I like that we put the no and I really don't want to. And that's kind of like, okay, why are you here? But thanks everybody. Appreciate your feedback. So let's switch back to the slides here and we'll get started. And you can I think I'll push this forward and I believe it will just leave us on the questions slide. So you put questions and comments there. So you're welcome to keep adding stuff there and we'll kind of check it as we have different breaks. Let me switch back to the slides and we'll get going. Okay, great. Okay, so thanks everybody for doing that. Hopefully fun, interesting survey, kind of tell you about sort of the audience members and some of the people attending this tutorial. So we'll jump past that. We'll go to the agenda here. This is kind of high level. We may not follow this exactly, but you know, we've kind of done an introduction, attendance survey, and we'll talk a little bit about, you know, what are SmartNICs, go into some more details. We'll focus on probably one particular type of SmartNIC that the tutorial organizers have a lot of experience with, but we'll talk about some of the other options that are sort of emerging. I'll talk a little bit about a few of the programming approaches. Then I'll hand it off to Oscar, who will share about some of the latest research. So some of those topics that we mentioned there, things like compression especially, people have done some interesting research in that space recently. Then we'll hand it over to Jeff Waugh, who will talk about TOCA MPI. We'll spend a little bit of time talking about security. That's kind of a newer topic that we're sort of thinking about, but we'll talk about some of the capabilities for that. Brief break, hand it over to Sergio, who will talk about OpenMP offload with their ODOS framework. and we'll show a couple of demos, and then we'll go through a couple, application experiences, with specifically the Bluefield 3 SmartNIC. This particular tutorial, we don't necessarily have a lot of hands-on stuff. We will have sort of some pointers to some demos that you can pick up, some code that you can look at. Part of that is just sort of infrastructure reasons. We are planning to do a little bit more of that for our SC24 tutorial. So if you're interested, stay tuned for that, and we'll share some more info on that. I think I shared this link, but we have kind of this webpage. This just has the agenda. We have put kind of a Google link to the slides, but at some point we'll have some version of slides that's there as well. Okay, great. So what do we hope you learn? First thing is, this is kind of HPC focused, but we'll talk about, what is a SmartNIC? What is a data processing unit? How can they be used as HPC AI accelerators? What can you do with them? We'll talk about, sort of the acceleration engines that live within a lot of these devices, and sort of things that we know they're good at and potential use cases, kind of near term and longer term. We'll go into depth on sort of one family of SmartNICs, the NVIDIA Bluefield, DPU, and we'll go, and talk about a lot of the different libraries and applications with that, and then we'll have a couple of demos that we'll go through. Excuse me. And I'll apologize, I'm a little bit sick, but hopefully we'll not be too noisy. Okay, so just to get started, just to give a high-level view, when we think about something like a HPC cluster or a supercomputer, we have this concept of, something that is a host is typically got some kind of XPU, so that could be a CPU, that could be a GPU. More recently, that could be an NPU, a neural processing unit, plus some kind of memory and storage. And then that host is sort of connected to other nodes via the NIC, the network interface controller. Obviously, we have this thing called the network. The network may vary depending on the type of system, whether it's a supercomputer, it has a very high-speed network, or maybe it's a data center or a more, traditional Beowulf type cluster. That network may vary, but the structure is very similar for all of these types of systems. When we think about a data processing unit, how that changes is that the NIC, instead of sort of just being focused on moving data and communicating data between hosts and different nodes, that NIC actually takes on some additional functionality. So here we have kind of this addition where the NIC has some kind of processing element. It could be something like a CPU. It could be something like a programmable fabric, an inline accelerator, and then typically some small amount of cache and storage. In that sense, the data processing unit is becoming a little bit more like the host in the system. Note that it can't really replace the host, and we'll talk about the complications of that, but it's providing this additional functionality that can be used to do some additional processing while you're moving data between nodes in the system. Okay, so some different examples of SmartNICs. We won't go into all of these. We'll touch on a few of them, and some of that is because some of these are products. Some of these have been announced but are kind of hard to acquire, and then some of them are being deployed more widely. The one that we'll talk about most today is the NVIDIA Bluefield. Some of that is our expertise. Some of that is because they're widely available. You can buy them and plug them into a system. A lot of storage vendors, especially, are starting to use them, so they're pretty widely used. Things like AMD, they have Pensando, sort of NICs, high-speed NICs, and of course Xilinx Alveo FPGAs, which can be used as programmable SmartNICs. Intel IPUs, infrastructure processing units, other kind of FPGA sort of cards. We have a few from a company called Silicom in our testbed that we'll talk about. Cards from Marvell, and then of course research products like Spin from ETH Zurich, which focuses on doing kind of a fast FPGA accelerated type SmartNIC. And I want to note as we're going, if you have questions, definitely please put them in the chat. We'll probably take your Zoom questions and also put them in the Slack as we can, just because that sticks around a little bit longer than the Zoom chat, but feel free to ask questions and we'll address them kind of when we get to the end of each section. So before we jump into this detailed dive into the NVIDIA BlueField, we kind of want to share what are some of the other options and how do they differ. So one of the most unusual ways to use a SmartNIC is to look at something like an AMD SmartNIC, i.e. a Xilinx Alveo-based SmartNIC. So we won't talk that much about Pensando cards, but here we have sort of an overview of what an Alveo SmartNIC running some kind of programmable fabric function like OpenNIC looks like. You'll see on the right-hand side here, we have both the card and the diagram of the flow that lives in the FPGA fabric. Sort of the key difference, you have something like a Pensando card, which has a fixed function. It supports a language called P4 for packet processing. We'll talk about that a little bit in a second. But the Alveo FPGA is really just a network pipeline, but then it has this additional functionality where it has user logic blocks. So, not only can it process packets, can it generate TCP/IP packets, but you can also do sort of custom packet processing. This is a little bit different than some of the other DPUs that we'll look at, in that here, it's very low level. You have to design that functionality yourself, but also, you have a lot of flexibility to do something interesting with that. You'll note in the corner here, we have a couple of links. So there have been some workshops and tutorials that we've run in the past. This slide, I think in particular, comes from one of those in 2023. So go check that out. Another example, Intel's infrastructure processing units. These have been announced. We haven't really seen a lot of these used in widespread use cases. They're probably available in data centers for hyperscalers, but when we think about HPC clusters, we don't have a lot of examples of these that have been fully deployed yet. But they do some of the same kind of things as sort of the AMD SmartNICs. A lot of these have an FPGA, so they can do high-speed packet processing. They also typically have like a small CPU, so you can do some additional kind of offload computation. One of the key things to note, and this will be different when we get to the BlueField, there's no OS support. So it's kind of a standalone device. It's doing a lot of packet processing, but you can't run generic applications on the IPU. Similarly, Marvell has ARM-based DPUs. They're focusing on very specific applications. They're looking at kind of storage applications, things like data plane development kit, DPDK, and looking at accelerating very specific functions like virtualization and offload for NVMe OF. Again, that's not something we're talking about in great detail today, but I think that's kind of one of the classic use cases for DPUs to help accelerate storage-based computing. And finally, note this final bullet, these are not really HPC focused. They're more focused on services. So, we'll see that there are certain features that make a DPU possibly more suitable for HPC. And then, there are also features that make them better for kind of service-oriented or data center type applications. Okay, so now we'll jump into a BlueField data processing unit or a SmartNIC. This is the BlueField. BlueField is kind of the canonical name for these, but they're all SmartNICs of some sort. If you think about sort of a high-level system, you might have sort of a host that has certain services, and then maybe you have a programmable NIC like we saw on the last slide, where you have some very specific functionality that lives on that NIC. That means that your hardware is very specialized for those functions. If we look at something like a DPU, the difference here is that it actually has sort of generic ARM cores and accelerators that you can interact with from a user level. So that means some of this functionality is more exposed to the user. It's not kind of a low-level custom interface. You can do a few more things with the accelerators that are on the car. Okay. If we think about how we might use something like a data processing unit, especially in terms of like an HPC sense, one thing we might want to do is we might want to run some kind of application on the host, and then we might want to offload some part of that to the DPU. If you think about traditional networking, obviously packet processing, offloading sort of custom accelerators to create and de-encapsulate packets is a good example of this type of offload functionality. But we can think about other ways to try to accelerate different functions that we don't want the host CPU to be working on. For instance, things like we talked about offloading sort of interactions with storage, writing things to storage, doing sort of metadata processing, maybe doing security, encapsulation, packet processing, and filtering. Also thinking about things like application telemetry, especially as it relates to sort of the networking characteristics of the application. Excuse me. Okay, so right now there are two kind of widely used versions of the NVIDIA BlueField, the BlueField 2 and the BlueField 3. They are both ARM core based systems, but the parameters are very different for these. So in one case, the BlueField 2, the max network bandwidth is 200 gigabits per second. That doubles with the more recent BlueField 3, which came out last year. Compute cores also doubles. The memory bandwidth, is dramatically increased for the newer BlueField card. And then, of course, some of the other stats for NVMe IOPS, close to doubles in both cases. One thing to note, although the BlueField 3 does have a lot more computation power, we'll see that it still is, sort of low-powered ARM cores, especially if you compare it to a high-end server-based CPU. So the BlueField 2, you would say, is maybe more like an embedded type, ARM core. The BlueField 3 is a little bit more higher performance, but it may not totally be like an HPC style server core on the card. All right, so we'll revisit our figure that we had just a minute ago, and the idea here is that you have sort of this one of the special things about the DPU is that you have all these libraries and software-defined interfaces coupled with sort of hardware accelerated features on the card itself. So we saw these different examples of different cards have different types of accelerators. NVIDIA BlueField has a lot of these different hardware accelerators in addition to the generic ARM cores. So things like compression engines, has some very custom inline processing cores, and then functionality and libraries for all these different features, from security to sort of packet processing, and libraries interact with storage and NVMe drives. One other thing to note here, you see this box on the right that says isolation layer. One of the design points of the BlueField is that it is actually sort of a separate memory space from the host. So if you think about it from a HPC perspective, that might be a little bit problematic because you have to transfer data between the host and the DPU. But that's sort of put there for security purposes. And we'll talk about some techniques and frameworks that have been designed to utilize data from the host and move it to the DPU to be accelerated in a high performance fashion. All right, so this figure is just standard NVIDIA kind of overview. I want to focus on the one on the right. When you look at in-network computing, there's sort of this focus on both having kind of security features across the networking stack, but there's also the split in terms of thinking about what functions live within the NIC, within a data processing unit, and then on the right-hand side, what things live within the switch. And so there are things like Sharp that are supported and supported in video switches. But on the left-hand side, you see that there's sort of generic functionality. There's this programmable data path accelerator, this inline accelerator, and then looking at some MPI type functionality to support HPC applications and any applications using MPI. So what are the caveats and what are the benefits? The caveats are that, as I mentioned, the host and the DPU are separate devices, and they're typically connected by PCI Express. So you have kind of this asynchronous communication, computation style. You need to think about how are you moving data between these two devices. If you're using them jointly for some kind of work, then you really need to think about how do you synchronize them. So that could be using some library or API like MPI. They could be using some kind of shared memory type feature, like using barriers with some kind of offload. But you really have to think about, okay, who has the data and how much time does it take to transfer between these two devices? One of the key things to note, as I mentioned, is that the DPU cores are less powerful computationally than your hosts. There's this concept of, okay, maybe I should just make my SmartNIC way more powerful, and then I can just make my host smaller. That is one concept. We would like to look at how do we accelerate applications so that maybe we can take some of the resources that we would need to allocate to the host CPU. But one thing I note is that these cores are not meant to totally replace the host. So they're designed in a way that they are computationally capable, but they may not have the extreme amount of memory bandwidth that a traditional server CPU might have. So you need to think carefully about what do you actually put on the DPU to accelerate. On the other hand, they also have very specific accelerator features. So you can have things like security encryption engines, you can have compression. These are all things that your CPU also can have, but may not have because it's not focused on optimizing and accelerating network traffic. So there are both limitations and benefits of using these DPUs. Other things to think about, the DPU is nice in that it can handle some things sort of without needing necessarily to interact and post things to CPU memory. So it can handle things asynchronously, especially as it relates to network traffic. You can send things from one DPU to another without interacting with the host, which can be really nice for certain applications. Again, that goes back to the asynchronous nature of the host and the DPU. If you're using the host and the DPU together, you need to think about that. But if you are looking to sort of optimize network traffic, that can be a nice feature to have. In a second, we'll talk about some of these terms here, things like cross-Gomami memory keys. These are sort of advanced DMA type features. And there are ways that you can optimize sort of moving data between the host and the BlueField. The other nice thing you might have noticed from the BlueField 3 sort of overview that I had, it does have its own DRAM memory, and it does have pretty fast memory in the case of the BlueField 3. This can be helpful in that you can store several gigabytes of data on the DPU itself. You can build things like lookup tables in memory and use those there. So that is also a supplemental resource that is nice to have that you don't need to interact with the host memory to use. At the end of the day, though, the thing to keep in mind is that you are always limited by the line rate. Basically, how much data can you send over the network and how much data can you receive at one time? Okay. Any questions from folks? Okay. So now we'll jump into a few of the BlueField acceleration engines. And first of all, we'll talk about this thing called cross-Gomami. So this is related to, we asked this question about UCC and UCX. And a lot of the idea there is that you're trying to efficiently set up RDMA or DMA type memory exchanges. And in order to do that, a lot of times you need to exchange a memory key, you need to set up a buffer region, and then use that to initiate transfers between either a host and a DPU, or in this case here, we have a host memory key that we're allocating. The network is getting a work request, and then it's using that to DMA data from a host memory to a remote location. So this is really nice. As we mentioned, the DPU can actually help initiate RDMA transfers without involving the host. So, we're taking some of that functionality that the host CPU might normally have to do and moving that to the DPU to accelerate it. This is a sort of a useful feature if you think about doing a lot of transfers between nodes, especially in an HPC type sense. This can be used to accelerate things like MPI as we'll show. Some other frameworks that we won't talk about as much today, but things like the data plane development kit, those have sort of different features and different support models. Things like cryptography, memory region encryption and decryption. Those are supported with the TPDK framework. Whereas this other framework, the SPDK, is mostly used for storage processing. So depending on the functionality that you're looking for, you might decide to use one or the other of these different frameworks. And we're happy to point you to more resources on those. But just as an example of what this looks like, we have here on the right this figure where we have kind of a user LAN SPDK, a kind of NVMe interaction, and then under the hood, it is using the data plane development kit and interacting with InfiniBand verbs. And in fact, that is probably living also on one of these lower level layers like UCC and UCX. There are a couple examples here, so we'll let you go and look at those if you have more questions about that. Okay, so one of the interesting things to note about the NVIDIA BlueField, we mentioned they have these different types of accelerators for crypto, for storage, for compression. They also have this thing called the data path accelerator. So when we think about a line-rated accelerator, we're thinking about something that needs to be very fast, but is very limited computationally. So we talked about the BlueField 3 has up to 16 kind of medium to high-end ARM cores that can be used for generic processing. They also have a small number of these TPA cores or RISC-V cores, along with an associated small cache system that can be used to very quickly process packets and do things like line rate processing. So there's a lot of interesting features here that honestly, I think we're still figuring out how to use. There is a really interesting paper that Oscar will talk about at SC24 that makes use of the data path accelerators. But these are kind of cores that you would think about if you have packets and you want to process them very quickly, but you may not want to do anything very computationally complex with them. Okay, and here are all the stats for those. As you'll notice, we should have put side by side probably the ARM core stats, but those are a little bit lower speed, but they do have very fast, low latency access per clock, as you see in the lower right part of this table here. Okay, so we talked about BlueFields. Now we'll jump into some of the high-level ways to program these before I hand it off to some of the other folks to talk about applications and research. Are there any questions that the folks have before we go on? Let's check the chat here real quick. Okay. If you have questions, please feel free to post them. Okay, so this tutorial is mostly focused on how do you think about SmartNICs with high-performance computing. Obviously with high performance computing, there are several different ways that you can sort of program those types of systems. We have things like distributed and distributed shared memory type frameworks, so things like MPI, where you're doing send receive, or OpenSHMEM or SHMEM, where you're doing put get based transfers. A lot of us know OpenMP, sort of shared memory, where you have sort of a single node or a single DPU in this case, and you're running an application across all the cores and some amount of memory within that system. And then this concept that we all know and love with things like TPUs, GPUs, CPUs, and FPGAs, accelerator offloading. And this is probably one of the most interesting applications that we think for SmartNICs. So we'll spend some more time talking about this last one, especially. If we think about how these get used for DPUs, we'll go through briefly the different types of programming. But in this case, we have sort of an MPI type model where you have ranks for each of the processes, and ranks can potentially be mapped to both host nodes and to the DPU. Obviously, the DPUs are a little bit weaker computationally. But one way that you can think about it is you just want to naively take an application that has some amount of parallel processing to do, and you just want to split that across different cores. You could say, I'm going to split my application and just run on a certain number of TPU cores and on a certain number of host cores. You may not get the best performance if you do that. A lot of times people look at this in terms of having the DPU handle some kind of I/O acceleration. So something like sending data to another node. We will talk about a use case for kind of the distributed model here with the MiniMD application that we did at Georgia Tech sort of later in the tutorial. With accelerator offload, there's sort of two ways that we can think about this. One is that the programming model can actually expose the accelerator and say, okay, this is sort of a device that you can offload to, or implicitly, if you think about something like MPI, where it is kind of another rank within the system. The first case where the accelerator is exposed is typically something like an OpenMP offload. Sergio will talk about that more in a minute. But the idea here is that you can either have the user explicitly think about how to interact with the DPU, or you can just say I have some service that is running there, whether it's some kind of accelerator or one of these DPA services, or something like an MPI job, and the user may or may not interact with it. In most cases, we find that for HPC, it's probably better to expose the accelerator because of that asynchronous nature and sort of the imbalance in computation between the two devices. And then, of course, there are other frameworks that we don't have a ton of time to go into. NVIDIA has a framework called DOCA, and someone will have to remind me what that stands for because I always forget. But that has a lot of these user level APIs that you can interact with. So things like the crypto, deep packet inspection, storage, the DPA interface. You'll notice on the left-hand side here, it also has sort of all these high-level APIs for using the DPU for orchestration, for application telemetry, and for things like software-defined networking. Some of the other accelerators that we looked at previously, like the Pensando and some of the other non-NVIDIA TPUs, also support P4. This is sort of a low-level vendor-neutral specification for packet processing. This picture on the right is from one of their, I think, tutorials, I believe. The nice thing about this is that it is vendor-neutral. It can be used on a lot of different devices. Potentially one of the bad things about it is that it is apparently very low level and is maybe inaccessible to people who are not experts in packet processing. Okay, great. All right, So at this point, I will hand it over to Oscar. I'll stop again to check and see if we have any questions. And I'll continue driving the slides here.
Thank you, Jeff.
Okay.
So this section of the tutorial, I'm going to be talking about SmartNIC research and the current state of the art. And the goal of this session is to highlight other people's work so that you are aware of what the community is doing in terms of SmartNICs. And then you can also reach out to these research groups to follow on a little bit more on their research. If we go to the next slide. So there are several areas that we have noticed that the community is exploring the SmartNICs, especially in the areas of programming models, but in particularly, we have seen research in the area of using the SmartNICs for task-based runtimes, where the scheduling component of a runtime is offloaded to the SmartNIC with the idea that the SmartNIC has a holistic view of the system and is aware of where to schedule tasks or move tasks around in a system, minimizing interaction with the host CPU, and basically this persistent aspect of basically a scheduler running on a SmartNIC can help improve loading balances issues, and in some cases track a little bit of reliability and rerunning tasks if they failed to run. There is some work done in that area, and that you can look at and follow a little bit on the link that is below the figure that talks about this work. There is also work that has been done in the area of the SmartNIC about how we can apply it for accelerating AI and machine learning workloads, in particularly either accelerating the communication aspect for a machine learning workload, or offloading certain aspects of the pipeline that is required for machine learning. We will talk a little bit more about that. The other area that we have seen use the SmartNIC is in the terms of use it as a unit for doing monitoring and performance tools, in the sense of using it as a way of understanding more about the workload in the node and using that information to tune the node and improve parameters and so on, with the idea that this tuning is basically doesn't interrupt anything related to what's happening in the compute node. And then the other two areas is in the area of data compression and acceleration storage. But the point that I want to mention is that there is a lot of areas of research in terms of use cases, and the fact that the SmartNIC is an isolated device that gives a lot and persistent across runs and jobs, that also gives a little bit of an advantage. And also the fact that it can be aware of have a holistic view of the systems can also, from the monitoring perspective, is also useful. And in addition to opportunities to do more research in terms of programming them, in this tutorial we'll focus on MPI and OpenMP offload, but there are other programming models also that can build on top of them, for example, like Cocos and PGAS models, like OpenSHMEM and so on. Let's go to the next slide. The next slide talks more
Oscar, I think we lost your audio a little bit. I guess we've, I think we lost Oscar. Yes.
That has direct access to the hardware.
Are you back, Oscar? Yep.
Jeff, can you hear me?
Yes. Yep.
Okay, apologies for that. Yes, we do have basically.
I think you're a little bit fuzzy though.
Okay. Yeah, so we do have applications that take advantage of data path accelerators. Let's go to the next slide.
Okay.
Yes, this is just to refer you to a paper that talks about applications using the DPA, basically to optimize collectives in terms of machine learning. This is a paper that is going to be presented at Supercomputing that talks about how they're using the DPA to implement a multicast protocol on the DPU. And if you go to the next slide, and the idea is that by implementing this multicast protocol, it can be used to accelerate distributed machine learning in the area of training, full sharded data parallelism. And the idea is that by using the DPA for this, we can reduce the traffic around, for this to implement this multicast operation by 2 times when applying this multicast protocol for operations like broadcast or scatter, reduce scatter operations. So that's a very interesting use case that currently is driven by the machine learning workloads and in terms of using the DPUs. There's going to be more information about that, and there's a paper that's going to appear at Supercomputing 24 that's going to talk more about that. We go to the next slide. The other area that we have seen about using SmartNICs or DPUs is to accelerate different phases in the neural network training, different stages in there. And the team led by DK Panda is basically exploring which phase can be offloaded to a DPU, and has been experimenting that when offloading the data augmentation phase to a DPU, there is a gain in terms of a speed of 13% in performance. So basically, this is not really optimizing per se everything, but it's basically offloading regions or phases in the deep learning stages. And there is definitely a work done in that regard. If we go to the next slide. The other thing that has come to our attention is that SmartNIC has also been explored in the idea of using it for telemetry, tooling and telemetry, with the idea that that there is a lot of system telemetry going on, and the DPU could be a good point to collect and adapt basically responses based on that telemetric to make the system more efficient, and also use it as a way of collecting information and visualize the information and so on. So this is some work that is basically being explored at AMD. And if you go to the next slide, and the idea here is that can we make the DPU as something to take smart decisions about the system resources and utilization, like collect the telemetric, tune on the fly, maintain, identify application signatures, and optimize things that's happening in the node. So that's definitely interesting type of applications that we're looking in terms of the DPUs. And then last, in the next slide, yes, so there has been some work in the area of compression in the BlueField-2 and BlueField-3 architectures, where it has been shown a group of researchers at the University of California, Merced, mentioning that there is the BlueFields can be used to optimize the compression by 101x speed up, and as a result, it can also improve communication latency by 88x per times. There is a paper that appeared at PDPS that talks about that, and I encourage you to read about it. But this is another way that is using the BlueField C engine compression basically to accelerate these components. And if we go with the next slide. Yes, and here it's a website that some websites that we are keeping track of what people are doing. Jeff Young and Rich Vuduc organized an event at CMPP 2024. It's a mini symposium where many researchers came and presented their latest research. And this is something that you can go and take a look about a little bit more about some of the work that I just presented. And also there is also other website that have the different research done that was part of a workshop at ISC on DPUs that also contains more detailed information of what I presented. And I encourage people to take a look at this sort of event so that you can see what people are doing in terms of SmartNICs. And with that, I give it back to Jeff.
Okay, thank you, Oscar. And just to let everybody know, there are a couple things. I don't know that we have any birds of a feather session this year at supercomputing, but there will be a couple papers there at Supercomputing 2024, and we'll also have a tutorial, a slightly different tutorial than this one there as well. I believe on Sunday, the first day of the conference. But there's a lot of research. There's also stuff here. Obviously, the tutorial before us talked about smart networking with DK and Hari and others. So go check that out as well if you missed it. Okay, great. So the next thing we're going to talk about, and I'm going to hand it over to Geoffroy, is how we think about MPI. So we're going to talk about both MPI, sort of distributed memory computation, and then also sort of offload with OpenMP offload to DPUs, and specifically to BlueField-based DPUs. Okay, Geoffroy.
Thank you. I would just start by briefly describe what are the different ways to take benefit of SmartNICs when you run MPI applications. The first thing to keep in mind is you don't necessarily need at first to modify applications. we showed over the past few years through different projects that it's possible to actually hide the offloading inside the MPI library or the MPI collective library. I'll tell you more about that later. But basically, just make it completely transparent for the application. Your application we still call MPI collective, MPI point-to-point, and the libraries, not your application, will actually trigger the offload, and you will be able to benefit from that offload without any changes. That said, if your application is not well designed, and not in a negative way, to take benefit of asynchronicity and this type of things, you may need to modify your application. And during the last part of the presentation, we would talk about that a little bit more with two different examples. I think the best way to think about it is to remember that SmartNICs are really used, at least in the context of MPI, as a asynchronous progress agent. So your DPU will be able to progress some collective communication, whatever it is, on behalf of your application that is running on the host and freeing the resources on the host. There is also a way to, an opportunity to do optimizations when we implement the collectives within the actual implementation of the collectives, but that would be a different topic. If you have interest in that, can talk about that offline. Next slide. So within NVIDIA, we did a bunch of prototypes. I was very much involved in one of them. So that's the slide about what we did. I was not the only one. So we support the collective that I mentioned on the slide, all-to-all, all-to-all-V, or gather V. So why these four collectives? Because one, we discovered based on our experience that this is where you have the most opportunity for performance improvement. And those are also very often the bottlenecks in scientific applications. So I'm not talking about AI here. OGatherV is kind of relevant for AI as well, but really the standard traditional HPC. And again, when you look at those four collectives is usually where the applications are spending a lot of time, especially as you scale up. And as I said, most of what I would talk about is assuming that it's inside the MPI library, mainly because it's what we know how to do. We are MPI experts in my team. So it's really enabled when you submit your job, when you write down your MPI run command line, you can ask for that offloading of the MPI collectives, and we have point-to-point too, but it's not public yet, not publicly available, I should say. And that is working with OpenMPI. So OpenMPI for us is the official version of MPI we use as a product. So if you're aware of what NVIDIA is doing, what Mellanox was doing before, this is called HPCX. So we continue to use that framework. And UCC, it was mentioned a few times, stands for Unified Communication Collectives. And that is a fairly new software package that is a reference implementation for collectives. Can be used for MPI, of course, but it can also be used for OpenSHMAM. And the work we did is within UCC. So again, by default, you don't need to change your application. I think that's important to remember. You can try to see what is the impact on the performance of your application without any changes. However, it is sometimes necessary to do modification to be able to leverage more asynchronicity and get the really nice performance. It really depends on what your code is doing, but something to keep in mind. Next slide. So that's a very brief overview of what type of performance you can expect. So that's with a macro benchmark. If you followed the presentation on the previous session, DK Panda actually talked about OSU quite extensively. That's a benchmark that has been around for a very long time. I think we all use it in the MPI HPC community as a reference benchmark. So On the left-hand side, you have the latency, and the right-hand side, you have also the latency, but at a different scale. So on the left-hand side, you have 1 ppm, which means 1 MPI process per node. The message size is medium size, it's 128K. And as you can see, with the blue being the host only, so what we all know traditionally, you run your collective from the host. And then with the green where we offload the collective, you can see a very nice performance improvement as you scale up. So by 32 nodes, you can see that you can get quite significant performance improvement. And if you increase the number of ranks on the nodes, you have the same type of pattern. So as you scale up, you can see some very nice performance improvement. So something to notice also, if you look at the legend here for the offload. So ASP is service processes, is the number of processes that are running on the DPU to do the offload. So depending on how much processes you have running on the host, you may need to have to partition these processes among several processes running on the DPU. So you don't create bottlenecks, right? So if you have 1 ppm, you can run one process on the DPU and they will connect to each other and the offload would be very, very straightforward. If you have a lot of ranks on your host, you will need to start to run more service processes on the DPU just to get the best performance from the hardware. And it kind of makes sense. Next slide. So that slide is about the non-blocking Auto-RV. And as you can see, we have very nice performance improvement as well. You can see also the interest of the benefit of having the asynchronicity directly available from the benchmark or the application, basically. So it means that all the stack from MPI and so on is really then designed to take benefit of the asynchronicity. And it ends up as being a huge performance improvement when you use DPUs. And this is the same platform, the same data size, and so on. Next slide. So this slide is about the overlap because this is something that is very interesting for most people when switching to DPUs. I want to remind you, though, that it's not necessarily the only matrix you can improve by using DPUs. It's the first one that comes to mind, but that's not the only one. And as you can see, by using DPUs, you can really have a nice overlap very quickly as you scale up. And that is very intuitive, right? Since you can offload the collective execution to the DPU, it frees the resources on the host. Next slide. So here it's actually a different thing that what the rest of the slides would be. So here it's what happens if you want to offload the entire collective to the DPU. So the entire collective will be initialized, executed, and terminated on the DPU. So it means that all the data that is required for the collective is pushed to the DPU first. The collective is executed, and the data at the end is, we ensure that it's copied back to the correct buffer on the host. So that is available in UCC and using UROM. So UROM is the part of Docker being the SDK from NVIDIA to use DPUs. So UROM is the package or the component that is used to manage services running on the DPU. So just to say that the UCC UROM component is really for that purpose, meaning offloading of the entire collective. That is directly available in the Docker SDK. And this is an example here. So it works for OSHMEM and it works for MPI. And again, the idea is really to push the entire collective to the DPU. And of course, doing it so you have 100% overlap because suddenly the host is not doing anything. And the interesting part is also you can see a performance improvement for the bandwidth, about 43%. And if I remember correctly, this is using Bluefeed 3. So even with a fairly straightforward approach where you offload everything, you can see that it's already very beneficial. You can see some very nice performance improvement. Next slide. Those are a few more details about what I just described. As you can see with URM UCC, so offloading the collective or the one-sided operation, sorry, to the DPU, you can have perfect overlap, 100%. And if you focus on the bandwidth, you can see that using URM UCC, you actually have a better utilization of the hardware, especially for medium-sized messages from 1K to 64K, where you can see in some cases 43% improvement in bandwidth. Next slide. So now I will talk about what we did in our group, which is a different model for offloading. So instead of offloading the entire collective, we started to offload only, we developed new algorithms for the collective that are pretty much designed for the DPU use case. So instead of having the host-only model where UCC is running in the context of your app and that the only thing that is going on, everything is triggered from the host, everything is processed from the host. In that case, we use UCC to push some functionalities of the algorithms, not all of them, some part of the algorithms, to the DPU. And of course, I will give a few details about what it means practically when I say that we offload some part of the algorithm. Next slide. So that's what the software stack looked like. So you understand also why we ask if you knew what UCX and UCC were. So again, if you think about the stack from NVIDIA or any other vendors, but I will talk about the one specifically from NVIDIA, there is no difference, right? If you take HPCX today, you will have OpenMPI, UCC, and UCX. So that does not change. So what we did is just extend those components, those libraries, so we could have DPU offloading. And there is one new library, Mimosa, that is really designed just to orchestrate communication and synchronization and interactions between the host and the DPU, but that's used within UCC. Another thing to notice is on the DPU, we try to keep the software stack as small as possible on purpose. And the idea is we try to minimize the noise created by the offloading service that we implement. And next slide. So those are more details about what it means about the versions of the software stack. So it's not entirely up to date actually, because UCX, if I recall correctly, if you use the very last version that came out not long ago, it will work out of the box. You don't need to have the specific version that is listed here. We had to have a specific version at first because we heavily rely on cross-GABAMI that was presented before, and that support was not yet released inside UCX, but it is now. And for UCC, we have a specific version of UCC for the DPU offload. We are trying to see what we can do to make it public and in the product, but I cannot give you details about this. If you're interested, feel free to contact us offline, and we'll be happy to help you out as much as we can. Next slide. So Mimosa. As it was said before, using the DPU means we need to have a tight interaction between the host and the DPU so that we can implement all new algorithms that offload in our context, the MPI collective, right? So we developed this new library just to make it easier. This is really the infrastructure. It is not the implementation of the actual algorithms of the collectives. It's really there to make sure that we can synchronize the processes that are running on the host and the DPUs, and nothing much more than that. However, we make sure that we have a good set of abstractions so that we can really focus on the implementation of these collective algorithms and forget about some of the details, and also to make sure that we expose all the information that is required to implement some optimized algorithms. So for example, you may want to implement your collective relying on the topology of where the ranks are, what are the service processes running on the DPUs, and make sure that you implement a algorithm that leverage all the hardware you have available the best way, right? Or the topology you have the best way. So a few terms that are critical centric to inside Mimosa. So we have this concept of daemon and service processes. So I already talked briefly about what is a service process. And again, just to make sure you keep it in mind, this is a process running on the DPU that provide a service, the offloading of MPR collective, for example. And your application can connect to it and start to offload something. Service configuration, it's just so that we can leverage at best the platform that you are using and the layout, I would say, of your job, since a job is usually only a subpart of the resources available on the platform. So we have inside Mimosa a mechanism that let us figure out what are the nodes that are used, what are the DPU that are used, and so on. And the user can then request different number of service processes for a specific job. And Mimosa will ensure that everything is set up properly. So the benefit of doing that is you can, if you want to experiment and investigate what type of performance performance improvement you can get using our libraries, well, you can start to run different configuration with different jobs and actually see the performance impact. So the other interesting concept in Mimosa is the concept of engine. So that's really a high-level object, I would say, that let us partition services. So when we implement the MPR collective offloading service, it's inside of a specific engine. And if you have another offloading service, you could implement that in the same service processes using two different engines, and they will be completely isolated. And the execution context, it's what is used inside Mimosa to manage communication between the host and the DPU. So it's a client-server model to make it easier. And all the communication are event-based. Technically, underneath, under the cover, it's a UCX active message, which is very beneficial because, again, progress is easier and more efficient. And we rely that VEVD to implement some of the communication that are used for the implementation of our MPR collective. And I will talk about that in a minute. Next slide. So if you look at, this is again just a summary, not necessarily much more information here, except that I introduced a few terms specific to UCC that map directly into MPR, but that are important when you look at the details. So on the host, you have OpenMPI, you have the collective framework within OpenMPI, and you have UCC. UCC internally have a few different concepts, and the two most interesting concepts in our context are the concept of teams, which are roughly the equivalent of a communicator. And I say roughly because a communicator is always a team, but the team is not necessarily always a communicator, MPI communicator. And the concept of task. So the task is a local representation. And when I say local, it's in the context of the MPI rank of a collective. Task does not have any global meaning. And so we modified UCC both regarding the management of the teams and the task to include some Mimosa primitive to actually implement our offloading service. So this is really how the offloading service for MPR collective is implemented. And this is why it's totally transparent to your application. And here I just mentioned event system and topology, because usually when you have communication between the UCC library on the host and the service process running on the DPU to execute the algorithm of the MPI collective, those are the two different components that are heavily used. So on the DPU, you only have Mimosa. You have a service process that uses the Mimosa library. And the Mimosa library, because of the way it's designed, remember I mentioned that all the communication are event-based. So the service process is waiting for messages based on the active message model, basically. It's a lightweight active message model. That's why I call it event and not active message. And when messages arrive from the ranks, would it be connection or start a collective or whatever, it will trigger handlers and it will unroll, execute the MPI collective. Next slide. So now if we step back slightly and we look at UCC, so that's the overall architecture. And as you can see, we did two modifications for the DPU support. That's the two boxes in blue. And so we try to have a very clean design, meaning that we don't need to modify the entire UCC library. Next slide. I already briefly mentioned all these points, so I don't think it makes sense to spend much time on it. So I would say just next slide. So the UCC code flow, and this is again just to continue the discussion. I mentioned the team creation, the teams and the task, but I think it's good to keep in mind the execution flow. So when you start to MPI application, MPI init, MPI will automatically load a component for the collective. In our case, it would be UCC. So for people who do not know the details, OpenMPI has a very modular architecture where things can be loaded dynamically and on demand based on users' requests. So in the context, again, in the context of UCC, the UCC library will be initialized. And the first thing MPI does is create MPI com world. So the communicator that represents the entire set of ranks for the entire application. So when it, in the context of the UCC library, it means a team will be created. So during that team creation, in the context of the DPU offloading, we will actually have connection to the service processes and the exchange of a few information between the rank and the DPU, so that the DPU can know what ranks are online, ready to go, and also start to create the topology that I talked about earlier. So this team creation, and that's the interesting part with UCC, is absolutely asynchronous, which is very interesting in our case because even if we have to talk with the DPUs, it means we are not delayed. And when the collective starts, the same way, there is an interaction with the DPU. And again, I will give a little more details in a moment. To just notify the DPUs, all the processes running on the DPUs that this collective started, that the ranks actually join the collective, and then we can execute the algorithm implementing the collective itself. And once the application finalized, MPI finalized, we'll actually call into UCC and finalize the entire library. Next slide. So if you think in terms of collective algorithms, I know I've been talking a lot about the actual algorithms of the collective, and this is an example. So I think initially when we wrote the slides, it was for OGADV, and a typical algorithm that's not necessarily the most efficient one is to implement an OGADV with a ring algorithm. So during the first step, you receive messages from the rank behind you and the one in front of you, assuming you have a modulo operation. And during the second step is to back, to in the front, and so on. So it's a very standard algorithm, very basic, that I think you can find in all implementation of MPI if you look at the OGADV implementations. So next slide. So by offloading that algorithm, that's what you can do. And here we assume the communicator is already created. So it's really when you start the execution of your collective. So rank 0 joined the collective. So it means that the rank 0 actually call MPI or GADOV, for example. It will send a control message post arrive to the DPU, to the service process that is running on the DPU. We call it control message because it does not have any data in it. It's really only an event to notify the service process that the rank joined the collective and provide a set of information about the collective. The service process will forward we send a message to the other service processes running either on the same DPU or the remote DPUs to say that it's ready to send for that specific rank. When remote processes receive that message, it will trigger a RDMA read using cross-GABAMI to move the data. So we are not in the control path anymore. We are in the data path. So it's moving the actual data of the application from the first host, from the host where rank 0 is running to the host where rank 1 is running. It can be the same, but it's literally moving the data. Once the cross-GABAMI operation completes, the service process acting on behalf of ranks 1 send a NAC to the service process acting on behalf of rank 0. And once it's done, we can send a DPU done message back to the host, which basically notifies completion for that specific step. So the interesting part again is by leveraging cross-GABAMI here, it means that the DPUs, the processes running on the DPUs can move data relative to your application without involving any of the hosts. So that's really important, and this is how we can get 100% overlap. Next slide. So the advantage if you have this type of algorithm, right? It's not necessarily for all algorithms, but it works well for large messages because we have a better utilization of the hardware. But it's not great for small messages because we have all these events going through between the host and the DPU and so on. It increases latency. So to address these concerns, we ended up implementing way more complicated algorithms that do not necessarily do only DPU offload and that are based on the size of the messages. So for small messages, we will use different techniques. And if the messages are large, we will use a DPU offload. And all this is within the API collective. Next slide. So security. So that's really a switch. I'm not talking about the offloading of API collective anymore. I know there is interest for security. This is why I included these 2 slides. I am not a security expert. So the best thing I can do is if you have interest in these things, contact me offline. I can put you in touch with the actual experts. But those are the features that are available on the Bluefeeds regarding security. From my point of view, the most interesting part are that you can offload a bunch of security-related features to the DPU, the same way I just talked about the MPI, the offloading of MPI collective. And for example, here it mentions IPsec and a few others, TLS, for example. But here again, I'm not a security expert. I will not claim I am. So I'll let you read the slide. And next slide. Same thing. This one is focusing on the physical protection. So getting closer to the hardware and what are the different features that are available. And if I remember correctly, that is for Bluefield 3. And again, I will let you read the slide and feel free to ping me offline if you have any question or any interest, and I will put you in touch with the experts. Next slide.
Okay. Thank you, Geoffroy. Yeah, so just to go back, well, the security, I think we're still trying to develop more material on that, but the takeaway, I would say, from this last slide, is just that there are a lot of different capabilities that you can use with, especially like a Bluefield DPU, probably more than we can get into depth here. But if you have specific questions, we'll try to capture those and find the right expert to help you out. Okay, so thank you very much, Geoffroy and Oscar. So I will hand it over to Sergio. We talked about kind of the distributed MPI UCC accelerated way to use DPUs, and he's going to talk about OpenMP offload to DPUs. So take it away.
Thanks a lot, Jeff. Okay, so yeah, I'm Sergio from BSc, and I'll talk about the OpenMP offload to DPUs. This is the outline of this talk. We'll see some. Well, we've already seen them in the previous talks, but yeah, we'll review the NVIDIA Bluefield DPU programming models, then OpenMP DPU offloading support with the framework ODOS, with a demo, also the ODOS MPI support with another demo. Finally, a use case that tries to wrap up everything and some performance numbers. Okay, so let's start. How can we program the NVIDIA Bluefield DPU? We have one option that is the low-level API provided by NVIDIA. It's called Doka. And to understand it, Doka is to DPUs what CUDA is to GPUs. But Doka is not an offloading API. And from our point of view, this is too low level for domain scientists. Scientists maybe prefer the MPMD programming model, multiple program, multiple data execution model in MPI, in which you can discriminate what to execute in each of the cores. Since the DPUs can be seen as additional processors, we can program that. The problem here is that the poor productivity that we can have because the processors are wildly different. So our approach is a DPU offloading programming with the standard OpenMP. So as we do when we offload our kernels to the GPUs, we could do the same to the DPUs. So using the pragma-omp target syntax, we can offload that the code to the DPU. This the pragma OpenMP, the OMP target offloads everything within the brackets to the target device. So we can discover which devices we have in the system using LLVM OMP device info. And in this example, in this system, we have a V100 in the device 4. But also in this system, we have a Bluefield DPU in the device 7. So if we want to offload to the DPU, it's as easy as setting the device ID to the pragma-omp target directive. Okay, so for instance, this is a simple MPI code in which we want to offload some computation to the DPU, and then just that. So we need to initially send the data from the host to the DPU, and that's why here we discriminate. If the rank is in the DPU, it will receive the data here at the beginning, and if the rank is in the host, it will send the data. Then, when the data is in the DPU, we can determine which rank is running this, and since we want to run it in the DPU, we have to select that rank. And finally, at the end of the execution, we will send back the data to the host. This is an spaghetti code and can be compacted into a lasagna code if we use ODOS. ODOS will allow us to use the pragma-omp directive to offload kernels to the DPU. In this case, we are selecting the data that has to be offloaded, and then we have here the kernel to run in the DPU. Okay, let's get into the details of ODOS. ODOS stands for OpenMP DPU offloading support, and this is its architecture. This is a host where we run a OpenMP target plugin in the host using using an extension of the Clang compiler for LLVM. And in the DPU side, we have the Docker OpenMP, a Docker OpenMP service running. So this the plugin and the service are communicated through the secure communication channel provided by Docker. ODOS is composed of 3 modules: the fat binary generation, the OpenMP runtime in the host, and the OpenMP service in the device. For the fat binary generation, we need to cross-compile because Bluefields are ARM architecture, and we can have it in a host, in a x86 host. So using the default Linux GNU GCC compiler, we can compile the binaries for those architectures and gather them in a fat binary. The target plugin on the host communicates with the DPU using the Docker secure communication channel, and it is responsible for sending commands to the DPU to start with to execute the load binary, the allocate and exchange data, and finally execute the target blocks, the kernel itself. So on the DPU side, we have the service, the Docker OpenMP service. It receives the commands from the host, from the plugin. In the case of receiving a command to load the binary, the service will save the image as a shared object. It will open the image and will send back the handle of the symbols to the host. If the service receives data operation commands like allocate memory, or send and receive data, so the service will run those operations. And when the plugin in the host sends the command to run the kernel itself, the service will use the handle of the image to run the kernel. Okay. So this is the first demo that we have for today. We'll start understanding how can we compile a Nodos enable application. Then we'll continue with some basic examples, the parallel feature of OpenMP, also how to compile with shared libraries, and finally a full asynchronous TCP example with a ping pong. For compiling an ODOS-enabled application, we will use the ODOS-enabled LLVM compiler, Clang, and then we will enable OpenMP and specify the offloading target. In this case, the ARM target because of the blue field. The result of this compilation is the FAT binary. So, for instance, imagine that we have this code. Here we are just offloading a print that says "Hi, folks." So at the bottom we have two terminals: the terminal of the host and the terminal of the DPU. What we have to do is to launch the service in the DPU that will keep listening, and when we execute the binary in the host, we can see that the print of the message has been offloaded in the service, in the DPU. Another example here, we are offloading a Pragma OMP parallel of printing a message again. So what we will do is launching the service here and then running the application. In this case, we have 16 messages printed because in the Bluefield 3 we have 16 cores. In the case of using share libraries in our applications, we will compile the share object in the host, as we usually do. Then we will cross-compile the share object for the target architecture, the ARM architecture, and finally we will link and generate the FAT binary. So this is like the previous compilation by step. And then we have this example, an asynchronous TCP ping pong that we offload to DPUs. In this setup, we have two nodes, each node with its own DPU. And what we offload in each of them is the TCP sockets initialization, the listening, the binding, the connection, and accept. And then we offload also the ping pong application itself. But for this, we have to distinguish between the client and the server. So when we run this code, what we have is that the host offloads the kernel here within brackets to the DPUs, and then the client sends the first ping, and the server answers with a pong. The ping pong function offloaded is this one. We have to check if who is running this is the client to start sending, and if it's the server, it will receive and then will compute for sending back the message again. In more detail, here we have the first row corresponds to node 0 and the second row corresponds to node 1. So node 0 is the server and the second row is the client. So we have to launch the Docker OpenMP service in both DPUs. Then we start the server, and when we launch the client, we see that the client sends the message to the server. The server receives the message. This is all happening in the DPUs. The host isn't doing nothing. And yeah, so on, the ping pong continues until the number of iterations. Okay. Those examples were nice, a nice proof of concept, but in HPC, we are more interested in MPI. So let's see how do we leverage MPI in others. By default, OpenMPI creates endpoints between the host that has to be communicated between the ranks. And if we launch an MPI exec, the internal architecture is this, an endpoint per rank in different hosts. So if we launch another MPI exec in the DPUs, we will have a replica of this setup. Then we can connect the communicators and all that stuff more higher level. But this is what's happening low level using PMX. What others does is to establish the communication, the cross-device communication, host DPU and DPU to host. Particularly, OpenMPI for others creates the endpoints in the PML UCX module of OpenMPI during the initialization, and when there is communication, the data is sent over those endpoints. So in this second demo, we'll see how MPI can be, how can we offload MPI communication with others. We are assuming in all the examples that we have 2 nodes, 1 rank per node, and have in mind that ranks can execute commands in the host and in the DPU. So the most simple example is a DPU to DPU point-to-point communication, in which we just offload the MPI send and receive, and we discriminate if the rank 0 is running the send or the rank 1 is doing the receive. Just as we would do host to host, but for DPU to DPU, we will use the Pragma OMP target. Now, if we want to cross-communicate the host and the device, this example shows how can we send data from the DPU to the host. So we need to offload this kernel to the DPU, and we have to create an MPI info object with the key remote destination heterogeneous enable to say to the runtime that this send is gonna be to another kind of device. It's gonna be cross-device send. So if we send to an heterogeneous, if we send with the remote destination heterogeneous, it means that if we are in a DPU, the destination will be a host. So rank 0 will send the data from the DPU, and this data is received from rank 1, from the host in rank 1. Okay? So this is, okay, with this example, we try to cover all the possible combinations. Host to host, device to device, device to host, and host to device. For this purpose, we have defined different messages that corresponds to different values to identify them better, because this execution is pretty fast. So we launched the service. We will in the two DPUs. So we need to launch it with MPI run -np2 in the DPUs, and then when we run the MPI application with MPI run again, but in the host. So the host connects to the devices, and okay, now let's see how it runs. to finally analyze the result. Okay, this is the end of the execution. And okay, the first example was host to host. For host to host, we sent and received the message 3310, and that's what we had. Rank 0 sent the message 3310 to rank 1, and it was received. The second example is DPU to DPU. So these messages are shown here in the DPU side because we have the rank 0 sent the message 3311 and rank 1 in the DPU received the message 3311. Okay? The next example is DPU to host, a DPU to host transfer. So the DPU here, the message 3312 send rank 0 in the DPU, send this to rank 1 in the host. And on the contrary, rank 0 from the host sends the message 3313 to rank 1 in the DPU. And here we have all the combinations. If we want to use collective across DPUs, it's as easier as just offloading the collective here. So in this case, we offload this, and all the DPUs will execute this all-to-all. Okay, then others also supports one-sided communication using MPI RMA. And in this example, we see a host to DPU put, RMA put. So for that, what we do is offloading the creation of the window and then the barrier. So the DPU will create the window and wait until the communication is done. Meanwhile, the host will create its own window, and rank 0 here will set the remote destination heterogeneous flag in the MPI info object to say that put this data from rank 0, the rank 0 host, to rank 1 DPU. Then we barrier again the ranks, and when it's done, this fence waits and the processes wait in the DPU are buried here, and in the host are here, and then the window is deallocated and the MPI info object also deallocated. Okay, let's see a more complex example using host DPU simultaneous RMA communication. Okay, what we are going to see here is that simultaneously we cross communicate the host and the DPU. So rank 0 host will put data in rank 1 DPU, and rank 0 DPU will put data in rank 1 host. So we have to start the service again in the DPUs. Okay, then we launch our application. It connects to the server, and then we have this. We can see that here the rank 0 in the host will put this message 3310 to DPU 1. It means to DPU in rank 1. And concurrently, although this scheme says that it's serially, we are running this simultaneously, as the example says. So we have these two puts simultaneously, and at the end of its execution, they are at the end of the execution, we have in the windows in rank 1 this value. But if we continue with this example and we do a simultaneous get, what we will have is that get from rank 0 in the host will get the value of rank 1 DPU, because we are always cross-communicating host device, and DPU 0, rank 0 in the DPU will take the value of rank 1 in the host. Okay, so these are the demo of MPI in Odos. Let's see the big picture. The big picture of this work. We are going to understand it better with this example, with a Halo exchange. This is a use case in which MPI rank has its own subdomain of a scientific application running, and a subdomain is composed of an inner subdomain, the outer subdomain, and a halo. So this outer subdomain is sent to the halo of the neighbors. So yeah, in this example, we are going to have two neighbors, left and right, and the outer subdomain is sent to the halo of the neighbor. So imagine this setup. We have two nodes. Each one with a GPU and a DPU. So in this case, logically we've assigned the massively parallel part of the subdomain to the GPU. So while the GPU is computing the inner subdomain, the DPU computes the outer subdomain and exchange the data and communicate the data with the neighbor. So in the second iteration, it will do the same. While the GPU is computing the inner subdomain, the DPU computes the outer and exchange that data. So this example could be coded like this. What we have here is to Pragma OMP target. The first one, okay, those are concurrently. We see that we use the no wait clause. And in the GPU, we are offloading the inner subdomain. This inner subdomain, yeah, we offload this kernel here, Pragma OMP target, with some GPU directives, and yeah, we offload that inner subdomain computation. We also offload here the outer subdomain and the halo exchange. We define the DPU ID of the device, and then here we have like the left neighbor and right neighbor. So that's why we have two tasks for computing this. And this, what we offload is this compute outer function that is responsible for, as we said, computing the outer subdomain, but it's gonna be like in the example was just one cell, but the outer subdomain it's not really big, and then it will asynchronously send and receive the data, the halo, the outer subdomain to the halo. Will send the outer subdomain to the halo and will receive in its halo the outer subdomain of the neighbor. Okay, and yeah, just to understand it better, some performance numbers here we have. We've used two different clusters. Just not to get into many details of the cluster, one cluster was equipped with Bluefield 2 with 8 ARM processors, and the second cluster was equipped with 16 ARM processors, newer ones, with a faster memory. For the software stack, we've used these software versions, and here for understanding better, we've leveraged the spec Axel benchmark suite. That one using that evaluates the OpenMP target offloading. We have modified a bit this benchmark, removing the distribute construct for GPUs and adding the SIMD construct for enabling SIMD instructions for the ARM processors. We've also created a variation of the OSU micro benchmark to support others. In the first comparison, this is just a proof of concept. We compare Bluefield 2 and Bluefield 3, and as we could expect, Bluefield 3 performs faster. The speed up is higher, so nothing new here. Okay, if we compare the OpenMP implementation against the MPI implementation of some of the micro benchmarks of spec Axel, we can see that the difference between them it's negligible. So it means that we are not adding overhead. As we can see here, this is a bandwidth test comparing standard MPI and others, standard MPI also, but using others, the offloading OpenMP. So this is a custom version of the OSU to offload MPI to DPUs. And we can see again that in general, the performance is the same. We have small variations depending on the packet size, but we are not adding overhead here. So that was all from my side. Yeah, if you want to visit Barcelona next October, we are organizing a hackathon and we can work on this together. Sorry for the spam. Thanks.
Great. Do folks have any questions about the Odos implementation or results? Check in the chat here. Okay. I think we have some other questions about OpenMPI and UCC on the Slack that folks have asked recently. Okay, for Sergio, here you go. In the OpenMP offload example, it looked like the device ID was a compile time constant. Can that be queried at runtime instead? Do you see that?
Yeah. Okay, yeah. There is no. Yeah, you can. We define it with a constant, but you can change it on the fly during. Yeah. There is no. Yeah, there is a demo code available on GitHub. Let me find it.
Yeah, I think the LLVM device OMP info command, that's where you get that device code, but it's kind of tied to where it's plugged into the PCI bus, I believe.
Oh yeah, that's why it makes nonsense to change it a lot, right?
Yeah, so it shouldn't change between runs, but if you have different devices, then
you have different devices, you can choose them.
Yep. I think the question is there demo code available on GitHub? There is a release of Odos.
Yeah.
So
let me get the link and I will paste it here in Slack or no in okay. Can stop sharing. Okay, there is a question here that says, in the MPI examples, are certain combinations faster than others? For example, DPU to DPU exchange faster than host DPU or DPU host? Yes, I didn't show it, but yeah, we experienced some variations in the performance when using a host DPU. We don't know yet why, but yeah, the faster was using the same DPU or host to host. We are working on that. We don't know yet.
It depends on your stack too, right? If you compare from a UCX point of view, so UCX between the host and the DPU, DPU to DPU, it's roughly the same. Not exactly, but roughly. But the
Yeah,
trick
makes
is always
sense.
the same, right? It's what your stack looks like, and this is where the complexity starts to show up.
Yeah, makes sense. But yeah, at the end of the day, it should, well, I mean, theoretically should be the same, but
Yeah.
okay, there's another question. Given the advancement in modern PI, one-sided, and hardware such as SmartNICs, have you done an evaluation comparing others with MPI? Okay, no, not SHMEM. We haven't compared it yet.
Yeah, that would be that might be a good research topic for someone
definitely.
who likes using SPIM.
It would be awesome.
Calling you out. I think there's been some work with SHMIM and DPs, but not enough. Not as much progress as with Odos. So there's not really a good comparison point for OpenSHMIM versus all the things that Sergio and his team have done with Odos.
There is a team at NVIDIA that was working on OSHMEM and DPU offload, but I do not know how much is public, but I can give a name. It's Manju. I think most of us know Manju. And he spent quite a bit of time on OSHMEM and DPUs.
Yeah, so I think there are people looking at it, but not a lot of publicly available implementations.
Yes, absolutely.
Yeah. Okay, great.
That said, Manju is also leading UCC, so there is more chance that there is something somewhere that can be used by everyone because he has his hands on everything. UCC and OSHMEM and the offloading of OSHMEM on DPUs.
Great. Thank you. Any other questions? Okay. So thank you very much, Sergio. If you have questions, feel free to keep putting them in the chat, and then you can answer those, or we can. Okay. Or if you have questions you want to put in the Slack, we have kind of some ongoing conversation there. So we've talked about some of the programming models. We've talked about sort of the distributed programming of DPUs. Sergio gave a great discussion of kind of the offload type model and sort of mixing that with the distributed MPI based model. We'll kind of wrap up. We don't have a lot of hands-on stuff for this particular tutorial. We're going to try to do a little bit more of that for upcoming ones, but we wanted to run through some of the applications that have sort of source code available that you can go and look at, previous sort of demos that you can kind of examine, and kind of walk you through, why those work, what's interesting about them, and then let you sort of go investigate those in more detail. I think we have a lot of questions, especially on the Slack, about, how does UCC and OpenMPI interact with other types of SmartNICs, so things like Pensando and Xilinx or Alveo SmartNICs. I honestly don't know that much about Pensando, so if we have somebody from AMD who wants to weigh in on that, feel free to. The Alveo SmartNICs don't really support like a full MPI stack or OpenMP offload. So, there's not really a way to target those in a similar fashion as we're talking about here. Part of the reason that these things like Odos work here is because there's sort of like a general ARM-based processors on a BlueField, and it runs an operating system. So it sort of has this substrate where you can, allocate memory and communicate between the two devices. But, those are all interesting things for future research. Okay. So I want to revisit one application. We talked about it a little bit in the past. We have kind of a shorter abbreviated version of discussion of this particular application. Jeff is going to talk about one or two applications, and then we'll kind of wrap up the tutorial and answer any other questions that you have. So this is an application where we're looking at mapping a high-performance computing code to a DPU. And in this particular case, we're not using the OpenMP offload model that Sergio just mentioned, because we did this work before, a lot of that was actually developed and tested and released. But this is work by Sarah Karamati in conjunction with researchers at Sandia National Labs. There's a paper about this that you can go and read. Excuse me. And we'll kind of walk you through what's interesting about this with respect to this implementation on a DPU. So MiniMD is a proxy app for a larger code, LAMPS, that is used for a lot of molecular dynamics type research. And it's one of these sort of, in-body codes where you have a lot of different particles that are in a system, and those particles are moving around. And so maybe these are, some kind of physics simulation, maybe it's some kind of, sort of biological simulation, but it has particles that have some position and velocity that changes within each discrete time step. All right. So if we think about this in kind of a distributed memory or MPI-based simulation, we might take this and we might divide it into sort of a symmetric, parallel region where each region gets mapped to a single processor. Then when we go through each time step, each of the processors is going to independently update the velocity and position for each of the particles, and they're going to calculate the forces on each particle from their neighboring particles. Finally, they're going to figure out the velocity, how fast are they moving, using these forces, and then use that as input to the next step in the simulation. So one of the key things to note is that with a lot of these simulations, we have this concept of a cutoff distance. That is, obviously, there are sort of strong and weak forces, but the particles that are closest to each other will interact more forcefully with each other, and ones that are farther away will have limited interaction with the particles, say on the other processors, for instance. MiniMD has a specific thing called a neighbor list that stores a reference to all the particles that are close enough to have kind of a strong interaction with that particular particle. All right. Each of these processes kind of has both these neighbor lists, but also has a boundary region between the processors that it uses that kind of encapsulates that cutoff distance and says, okay, even though these particles are on a different processor, these are also ones that may impact the velocity of this particle in the next iteration. So we have on the left-hand side, we're kind of building up all the pieces of this algorithm. We have things where we update the velocity and the position. We change the velocity. We say, what is the force on it from other particles? And then we're building this region of who is near me in each iteration. Then at some point, as the particles move, we have to update that list of neighbors. If you do that too frequently, then you slow down your simulation. If you do that too infrequently, you likely get results that are not very accurate. So there is some trade-off in terms of how often you actually want to update this boundary region between particles. And then finally, you have to do updates at some point, and this is actually the part of the algorithm that is most communication intensive, especially if you're exchanging data across processes. So that's why we have this extra buffer around the region, that is interacting with each particle. So MiniMD specifically calls this like a skin type parameter. So one of the things I note is that we have this simulation that has these discrete steps, within each iteration. Some of these things can be done in parallel, and they can be done in parallel on different processors. But between iterations, there are actual serial dependencies. So, for instance, the neighbor list generation is one of these serial dependencies that we have. But there are some things that we can do, kind of independently, that we can potentially split out. So, for instance, the force computation, we can do that while we're building the neighbor list for the next iteration. So, in this work that Sergio did, one of the things she looked at was trying to figure out which piece of the algorithm could actually be moved and offloaded to the DPU. And here, remember again, we're not using OpenMP offload. So this is more of a very manual process using MPI and OpenMP, as we'll show in a second. Okay. When you move the force computation, you also have to do additional communication. So you have some additional overhead, and then you have some reorder operation that you need to do to make sure that the DPU also has all the information that it needs from each iteration in terms of updating the neighbor list and the border list. All right, so again, we ran this on some systems, the HPC AI cluster. Unfortunately, these aren't online at the moment, but I think maybe Thor is online. But it has Bluefield 2 DPUs. We'd like to replicate this with Bluefield 3, but haven't done it yet. But I think the results would be, should be representative. So one of the things about this restructured method is that, the code was sort of MPI plus OpenMP based. We took part of the algorithm and moved that explicitly to the DPU. We didn't necessarily do OpenMP offload. We think that might be a lower latency way, especially from a programming, ease of use way. It would be easier to do, but it might be a little bit lower latency to do that. Here, this is more like a rewriting the algorithm or restructuring the algorithm type optimization. But when we do that restructure, we find that we do get speed ups on the Bluefield 2 from moving that force computation to the Bluefield device. One thing that we note is that, we talked about this trade-off in terms of if you make your SmartNIC too big, you've just made another, host node. And the SmartNIC itself, the CPUs on it, are not, quite as computationally powerful as your host server CPUs. But, they provide a nice sort of offload acceleration that you can use in conjunction with your server side. So here we've noted that, say, if you had, you have to have a NIC anyways, but say if you added a Bluefield 2, you might be able to get, a speed up of up to 20% for a very small incremental power increase. I think we estimated the 6% based on plugging in the Bluefield 2 as opposed to having no NIC. But the idea is that the performance per power benefits may be very favorable in some cases for some applications. Then if we look at the kind of hybrid MPI and OpenMP performance improvements, here, we're looking at how long does it take. So less time is better. And this is kind of interesting in that we compared this against running on the host node itself. So you'll see sort of this teal green line here. This is basically no offload. And so you note that if you use all the cores on the host, it's faster. And you might expect that. This is a server grade CPU, and you're comparing it against a DPU, which, in this case has 8 ARM cores. I forget exactly the model number on them, but Bluefield 2 is a little bit slower than a Bluefield 3. But it's never going to be able to match the raw computational power of the host server. However, what's interesting is that you kind of see these points where you have sort of a knee of the curve where the running time of the neighbor build on the host and the force compute on the blue field are very similar. So you're getting, very good parallelism. If you had, say, this many number of threads running on the blue field and this many number of threads running on the host. So let's look at the bottom case here. Here we have, 8 threads running on the blue field, and we have 4 threads running on the host. So in that case, you could see where you could use the blue field to get some acceleration rather than taking up a whole CPU to run this application. Sorry. Okay. If you want to check this out, we're not going to run through it in detail, but this is from our SE tutorial that I think Hamid actually shared. Thank you so much. But the code is there. One of the interesting things about this, if you look at this versus what Sergio shared with the Odos kind of offload, here we are actually running 2 different applications. So we're running an ARM-based application that we built on the DPU itself, and then we built the same code on the host, and we're running kind of a split MPI job. So they're actually talking to each other using MPI communicators. That's a little bit different than sort of the LLVM target offload model with Odos. That's probably a little bit easier to do. This is kind of quirky to set up and run, but it does work. So it's kind of interesting that you can go through and run that and see how it works. We do have the source code here, and you can look at it and see how we move the force calculation to the blue field. Okay, so where do we go from here? This is an idea where we took an algorithm and we restructured it explicitly for the blue field. We believe that there are other HPC applications that may map well to this. One of the things that we're looking at right now that we don't have a ton of data to show, but that our student Sarah is working on, is looking at implementing Maxwell equation solvers as typified by a framework like Moodle, and using that as kind of the basis for trying to find additional things that we can parallelize using the DPU. So on the right-hand side, we have kind of this complicated looking solve, and you'll notice that we have sort of these different steps in blue that are sort of preparation and sort of post-processing type steps. But then in the middle, you have these 2 sort of computation pieces, and one of those may be a potential offload candidate. So right now what we're looking at is seeing sort of in the same way, can we take that portion of the code that might typically run in parallel, say on a CPU, with using something like OpenMP, and then map that to the DPU and see if we can get acceleration by doing that. So obviously this approach may not work for all applications, but this is one way that you can think about how you might take a HPC application and map it to a DPU. Okay. Any questions before I go on? Okay. Great. So I'll hand it over to Geoffroy, and he'll talk briefly about 2 codes, Octopus and P3D-FFT. And then we'll wrap up.
Thank you. So 2 different applications to illustrate 2 different use cases, and you will quickly remember what I said earlier. So the first use case, Octopus, the first application, let's say, we did not change the application at all. And we can show that there is actually some nice benefit, and I will explain in a minute what that slide is. And in the other case, with PT3FFD++, we actually changed the application. So with Octopus is a code that is actually fairly popular for different simulations. Don't ask me the details. I'm no expert. I'm not a mathematician or a computational scientist. I'm just a computer scientist. But the point is, it's real application, real input, real simulation. So as I said, no modification whatsoever. We ran on 32 nodes, 100 steps, and that was running on Thor. So you heard that name before, that the cluster that was available on the console, the AI and HPC console group. And we compared the offload with two different configurations of MPI. So in purple, you have HPCX. So as I said before, that's the official MPI stack from NVIDIA. And we have OpenMPI. So here the difference is with OpenMPI, that's a newer version of OpenMPI that is used directly from the version directly from upstream, so from the community. So, and we ran different configurations, so OS 32 nodes, OS 100 time steps. But in one case, we use 8 ppn per node, so 8 MPI processes per node, and in the other case, 4 MPI processes per node. These two numbers are directly driven by Octopus. That's a typical configuration for Octopus. It's not a choice we made. And for the OpenMP thread, because it's an MPI plus OpenMP application, we have two different configurations between 4-thread and 8-thread. Why 4 and 8? It's because we discovered doing some experiment that the number of threads, these two numbers are the best configuration for the number of ppn. So we decided for the number of ppn first based on the constraints from the app, and then we set the number of threads to find the best configuration. But the point is, as you can see, even without changing the application code at all, you have a nice speed up with when you offload the MPI collective to the DPU. So next slide. And here you have some of the details about where that speed up is coming from. So we had basically two different collectives that were offloaded, OGATV and ALT-WAL. MPI wet all was not offloaded, and MPI, of course, and MPI all reduce was not offloaded either. And as you can see, the interesting part is just by using collectives that are offloaded to the DPU, even if it's not all of them, you can actually change the way the application is running. So if you look at the profile, it will change the way ranks join the collective operation, exit the collective, do the computation, and so on. And ultimately, you have that significant improvement. So even if you don't have MPI, non-blocking MPI collective, and you are using the offload, you may actually see some significant performance improvement for your application. So next slide. However, that's not always the case. And this is where we talk a little bit about P3D FFT++, because for that package, that application, we did not see the performance improvement out of the box. Next slide. So what a colleague of mine did, Dimitri, he took P3D FFT++, and he's the main maintainer for the project. I think he's even the one who created it years ago. And he started to think about how we could change the actual implementation to have a more, to be able to leverage DPU offloading. So I will not go through the details of P3D FFT++. I think most of us understand what is a fast Fourier transform. That's one of the very well-known package for that. And if you're interested, there's a bunch of details here. So next slide. So what Dimitri started to do is try to see if he could modify P3D FFT++ to include some overlap. So again, not being an expert, but the thing to understand is when you execute P3D FFT++, you have different stages. You have 3 compute stages, and then 2 communication stages. And I have a small graphic on the next slide that I will show in a moment to illustrate that, but they were basically executed in a very serial manner. So the other thing to understand with P3D FFT is it usually uses internally some independent variables. So what Dimitri tried to do is see if he could overlap the operation on these independent variables to try to have overlap. So next slide. And that's what it looks like. So the first graphic where you have one bar, it's really the serialized execution of the different phases, computation and communication, that were initially implemented by the code. And it changed the code so that it could handle the independent variables independently, because they're independent, and offload the execution of some of the collective that are required for the communication phase for each of these independent variables. Next slide. A slide is missing. But basically, yes, you can see that you have a nice performance improvement for P3D FFT. And if you look at the breakdown, you see the same thing that what I showed for Octopus, meaning that the execution of the collective is faster. And since now you have this parallel computation or execution of these phases for multiple variables, you actually see a significant speed up at the end of the day. So again, that was just to illustrate the two use cases, the two extremes. You don't need to change the application and you have a nice speed up, or you actually need to change your application to see a nice speed up. That's it.
Okay. Sorry about that, Tifa. We might have had a merge. We might have had a merge issue.
Yeah, that's okay.
We'll get that back in there. I think one thing to point out too is that if I believe it's one of the branches of P3D-FFT. If people pull that.
Exactly. So the code is absolutely available. You're absolutely right. The reference is on the slide, so everybody can access it. And of course, as usual, if you have any questions, just ping us.
Okay, great. All right. Thank you for bearing with us for technical difficulty, and thank you, Defwa. Okay, so we've kind of talked about, we've talked about the different ways that you can sort of use DPUs, the different types of SmartNICs and DPUs, and we just really want to wrap up and kind of let you know. Obviously, these slides will make them available, but one of the big questions is sort of, there are two questions that people typically have. One is, what is kind of the ongoing research that people should look at and think about. In that case, I think you can tell there's a lot of sort of underexplored, especially with things that are not NVIDIA Bluefield based frameworks. A lot of the other SmartNICs don't have quite as many pieces or frameworks with them, so they tend to do a little bit more low level or do sort of P4 type implementations. As someone pointed out in a question, sort of evaluations of the impacts of SmartNICs and DPUs on sort of AI models, either using things like UCC. Jeff pointed out in the Slack that if you're looking at doing sort of CUDA-based things, you probably need to use something like NVIDIA's Nickel to actually implement that, rather than UCC, because MPI is not necessarily compatible with CUDA streams yet. So there's a lot of active research and engineering to make these devices more useful for HPC and AI applications. If you would like to do that, there are a couple ways to do that. I run a test bed. It's called the Rogues Gallery. We have a couple Bluefields. We have some Alveo FPGAs. We're looking at things like OpenNIC and another project called RicoNIC on the Xilinx FPGAs. Oscar from Oak Ridge works with some folks who run a testbed called Wombat. They have a few Bluefield devices. And then if you are interested in stuff like AMD SmartNICs, Xilinx has a couple of these centers called Hack or Exact centers, I believe. I think there might be a few other sites that we have not put here. I believe maybe some folks in the UK at Durham also have some DPUs. If you go to one of the links that we put earlier in the SmartNIC research page, then it has some additional resources there that you can find and evaluate. So at that point, we're pretty much out of time. We are coming up on the next tutorial here. Are there any questions that folks have, or anything that we covered that you'd like us to talk a little bit more about?